Welcome to our presentation. I'm Abhijit from the Department of Electrical Engineering, Indian Institute of Science, Bangalore. Our presentation is titled Differentiate and Fire Time Encoding of Finite Rate of Innovation Signals. We consider the problem of sampling and reconstruction of continuous time signals. Since the problem is ill-posed, the usual scheme is to consider a suitable structure on the signal. Classically, Shannon considers signals with compactly supported Fourier transform, which leads to the Shannon sampling theorem. This is a cross-section of the human brain, and in particular, the parts pertaining to the human visual system. Vision incident on the retina is transferred to the lateral geniculate nucleus, and from here, vision is transferred to the primary visual cortex. Human vision is encoded in two pathways, the parvocellular and the magnocellular pathways. The parvocellular pathways motivate the integrate and fire scheme, and we propose the differentiate and fire time encoding machine motivated by the magnocellular pathways, which are responsible for transient vision. In this paper, we consider time encoding of continuous time signals, which is an alternative paradigm to uniform sampling. In time encoding, the signal is encoded by a sequence of time instants as opposed to a sequence of amplitudes. We illustrate the concept of time encoding in figure 2, where the signal y of t is encoded using the trigger times t1, t2 through t10 that correspond to events. Time encoding is attractive as it mimics peripheral perception of sensory signals. The hardware required for time encoding require low power, and further, they give sparse and measurements with low redundancy. We formally define a time encoding machine, or TEM for short, as a mapping from a function space to the space of sequences that contain trigger times. A TEM is equipped with an event operator and a sequence of reference functions. A TEM takes a continuous time signal and gives a sequence of time instants called trigger times that are ordered and satisfy the characterization, that is, the samples of the transform signal EY and the nth reference function meet at the nth trigger time. The output sequence has two properties: the sampling density, which is the supremum of the difference between two consecutive trigger times, and we say the trigger times are epsilon distinct when the difference between the consecutive trigger times is at least epsilon. In this talk, we enlist in detail the contributions of our paper. We will define the differentiate and fire time encoding machine, or DIF-TEM for short, and its properties. We will then see how FRI signals are encoded using the DIF-TEM. We will provide sufficient conditions for perfect recovery. We then move on to demonstrating the claims via simulation results, and in the end provide conclusions and future work. Figure 4 shows the schematic of a differentiate and fire time encoding machine. The input signal y of t is given to a differentiator. The output of the differentiator is added to a time-varying bias Bn of t that is also a function of the nth trigger time. The sum V of t is passed to a non-inverting Schmidt trigger with symmetric thresholds at plus and minus gamma. The output is a bilevel signal that transitions at the trigger times. For the rest of the discussion, we assume that the trigger times are available to us as the output of the DIF-TEM. Figure 5 shows the DIF-TEM with a linear bias term. Whenever the input to the Schmidt trigger reaches plus or minus gamma, the corresponding trigger time is available at the output and the bias term resets. We now consider the properties of the output of the DIF-TEM. The lemma T-transform gives the relation between the samples of the derivative of the input signal and the output of the DIF-TEM. When the input to the DIF-TEM with parameters alpha and gamma is a continuous function, the samples of the derivative of the input signal can be computed using the trigger times and the parameters of the DIF-TEM using the simple relation. This allows computation of the samples of the derivative signal post-signal encoding. A corollary to the T-transform is the following stability result. If we further assume that the input signal is continuous with bounded derivative, we can show that the difference between the consecutive trigger times is bounded above and below by values that are dependent only on the parameters of the DIF-TEM and the bound on the derivative of the input signal. We now have a bound for the sampling density and knowledge of the epsilon distinctness property of the output of the DIF-TEM. We now consider differentiate and fire time encoding of finite rate of innovation signals. We consider the prototypical T-periodic FRI signal composing of a known pulse with k unknown amplitude parameters C sub k and k unknown shift parameters tau sub k. The rate of innovation of the signal x is 2k by t. The signal is better analyzed in the Fourier-domain. The Fourier series coefficients have the familiar sum of complex exponentials or SWC structure that is familiar in spectral analysis. Now, with the knowledge of the Fourier series coefficients, the signal reconstruction problem is a parameter estimation problem. We use the classical Prony's method for parameter recovery. Prony's method consists of an annihilating filter that has roots at e power minus j omega naught tau k, and it can be shown that the result of the convolution of the annihilating filter and the Fourier coefficients gives 0. In matrix form, the annihilating filter is a non-trivial solution to the equation xh equals 0, where X is a convolution matrix constructed using the Fourier coefficients. Once the annihilating filter is found, the roots are in one-to-one correspondence with the shifts. To obtain the Fourier coefficients, we propose kernel-based time encoding. Figure 8 shows a schematic of kernel-based time encoding using a kernel G of t. The filtered signal y of t is also t-periodic with scaled Fourier coefficients. We then select sampling kernels that satisfy the alias cancellation conditions, that is, uniform samples of the Fourier transform of the kernel evaluate to a known non-zero value gm on the integer set minus m to m and 0 outside. An example of a kernel that satisfies the alias cancellation condition is a Fourier-domain sum of sinks or SOS kernel. In this case, we see that gm can be set to 1 over the integer set. Using the t-transform, we compute the samples of the derivative of the filtered signal, which has the following relation with the Fourier coefficients. We note that the relation can be put into a linear system of equations of the form y equals gdf times s times x hat, where s contains the scaling terms j omega naught m, and the matrix gdf can be shown to be an invertible matrix when L is greater than or equal to 2m plus 1. We also note that the diagonal matrix S is singular since the m plus 1th element is 0. We solve by resetting the entry to 1 and considering the 0th Fourier coefficient to be 0. This is a drawback that is seen across derivative-based sampling methods, where the signal can only be recovered up to a constant. For Prony's method, we require 2k plus 1 Fourier coefficients. To obtain L greater than 2k plus 1 measurements, we enforce L times the sampling density to be less than the period t. We summarize the sufficient condition in the following proposition. T-periodic FRI signals observed using the sampling kernel G of t that satisfy the alias cancellation condition and a DIF-TEM with parameters alpha and gamma provide a sufficient representation of the FRI signal if the parameters satisfy the following relation. To support our claims, we consider one periodic signal with 5 scaled cubic B-spline pulses. We observe the signal using an SOS kernel and parameters critically set to satisfy the sufficient condition. In figure 10, we see that the reconstruction X check gives superior reconstruction as compared to a simple integrator-based reconstruction with a reconstruction SNR of 51 dB. We also consider a one-periodic stream of 5 Dirac impulses that are observed using the SOS kernel and parameters critically set to satisfy the sufficient condition. In figure 11, we see that the reconstruction X-check is perfect up to numerical precision. In summary, we considered differentiate and fire time encoding of FRS signals. We proposed kernel-based time encoding and analyzed sampling and reconstruction in the Fourier domain. We demonstrated that perfect reconstruction is possible using samples taken at the order of the rate of innovation of the signal. Here are some key references, and we would like to acknowledge the Prime Minister's Research Fellowship, Pratiksha Trust, and the IISc Institute of Eminence funding for their gracious support. Thank you for your attention.